All right, so last up is the review session for basically the entire course. Um, so big picture thing. I'll just talk about the final exam first. So we dealt with conduction for a month, we dealt with convection for a month, we dealt with radiation for a month. In general, real world problems, you're going to have all three combined together. And so that's kind of what your final exam is going to encompass. I'm going to have basically one real world problem. It's probably going to involve all three modes of heat transfer. It's also a real world problem, meaning that there is not necessarily only one answer. You can make all sorts of assumptions. You can kind of approach it different ways. And so there's not necessarily one right answer. It's more about how would you go about solving this problem. And so it's more about you describing this is what I'm doing, as opposed to actually get a answer of whatever the answer you think, whatever it is. It's not like I'm going to have an answer of, oh, the answer is 5,000 watts. It's, there's different ways you can approach this. There's different assumptions you can make. There's different ways you can calculate things. I just want to see which way would you do it. So because of that, it's not only open book, but you are actually allowed to use the internet for this one. I don't care if you use the internet, you can do whatever you want. But again, the only thing you can't do is talk to other people. So I don't want you sharing answers. I don't want you working on this in teams. I want you to work on it by yourself, but you can use anything you want other than other people. Again, technically covers all the material, so you will probably have to deal with some conduction, some convection, and some radiation, but primarily focus on just the basic parts of those. So the actual exam, what it's going to look like is I'm going to give you this real world problem. And what I want back from you is kind of I'm going to call it a report, but it doesn't really need to be a report. It's, again, be bullet points, could be figures, could be equations. Basically has two parts to it. First part is, from this basic description I give you, how would you go about solving the problem, in the sense that what is the overall energy balance? What is the overall stuff's going on? What are you neglecting? What are you assuming? All those things set up the problem and derive the overall equation to be solved. Then the second part of that is actually solving this equation. So now I have this equation. How am I going to solve it? Am I going to do, is this a case of forced convection? Is it over a flat plate? Is it this scenario? Is it that scenario? What equation am I going to use for H? Those sorts of things. Can I solve this equation mathematically? Do I have to do it numerically? What am I going to do for that? So that's kind of the part two of it. So again, describe how we do that. And again, it's the description of this that's more important than the actual solution. So if you just want to describe it first and then work on how would you actually do it, that's the way I would go. I wouldn't try to actually solve it first and then describe what you did. I would do it the other way. So describe what you're going to do, try to do it. If you make it through that and get an answer, great. If you don't, at least the description is there of what you are doing. So as I mentioned, heat transfer, three basic things: conduction, convection, radiation. We spent a lot of time dealing with each of those individually. Now I want something that has all these three things together. So in general, I could have something like this. So my scenario is I have this plate. It's being heated from the bottom. So there's some conduction coming through from the bottom, has some flow over it. So there is some convection being taken away from it. And then there's also some radiation. So there's some surroundings up here. And so my general overall energy balance, I'm going to have some conduction coming in, convection and radiation going out, possibly depending on scenario. I could have this plate being heated up or cooled down. So some of this energy could be being absorbed into the plate, and that's a change in temperature of the plate itself. So is that involved? Is it not involved? So for this particular situation, energy going in from conduction equals energy going out from these other sources: convection, radiation, and energy being absorbed into the plate itself. So this would be my energy balance equation for this particular example. It's not necessarily the overall energy balance, because again, it depends on what's coming in, what's going out. Is this thing here or not? Are these things here or not? So do I worry about radiation? Do I not worry about radiation? Is there convection? Is there free convection? So again, that's kind of the part one of this. How do I set up the overall energy balance and get to some equation that I want to solve? The next part of it is how to actually solve this. So how do I actually What sort of convection am I dealing with? What are my shape factors? What are my emissivities? Is this involved at all? What sort of conduction am I dealing with? And so that's when we get into the more basic stuff of basic conduction. I have this minus Ka dt dx. That's for rectangular surfaces anyway. So did I give you a rectangular surface, or maybe it's a cylinder surface? So for cylinder spheres, I'm going to need to use these sort of equations. If I'm dealing with cylinders with spheres, I could also deal with maybe a total overall thermal resistance. Maybe there's convection and conduction and another convection side. So again, can I deal with this total thermal radiation and total overall thermal resistance, and can I do it that way? And that way deal with both radiation, that way deal with both conduction and convection at the same time. So that's another possibility to deal with those. Do I need to calculate any of this? The answer is no. So how am I going to deal with that conduction part of it? To get to convection part of it, how am I going to deal with that? Again, am I dealing with a flat plate? In which case, is it a flat plate? Is it horizontal? Is it vertical? Is it laminar? Is it turbulent? How am I going to find H for that scenario? Is it a tube? Do I have flow going through my tube? In which case, again, I have this part where entrance and exit temperatures. I'm going to need to worry about, is the fluid in here actually heating up? In which case that last term, m dot Cp delta T over time, fluid heating up part of it, that's going to be important. So if I'm dealing with a tube, then I'm probably going to have to deal with this term here, because the fluid is going to be heated up. Do I need to deal with that in other terms or other geometries? Who knows? So that's, again, things that you're going to need to figure out and describe to me what you're doing in part 1. So again, for this tube part, I'm going to actually probably need these m dot Cp delta T equations, and that's going to equal my convection being convected away. But of course, this is just a simple, I'm only dealing with convection. I could also have some conduction and some radiation terms over here as well for the case that I'm going to give you. There's also free convection. So again, my plate is vertical. Do I worry about the convection currents from buoyancy? Are those big? Are they small? Because it could be either. So again, it's up to you to decide whether you want to include that or not. And finally, radiation, basic radiation. I have sigma A T to the 4th power as my overall heat being transferred. For the purposes of this project, don't really need to worry about too much radiation networks and insulated surfaces and things of that nature. Don't need to really worry about more than 2 objects. Because I'm only dealing with 2 objects at most. For example, that plate that we saw at the very beginning, that plate was interacting with the surroundings. So that's all it was interacting with. It wasn't like there's 2 plates and surroundings, things going on. So all I really should have to deal with are epsilon values, maybe shape factors. But again, if I'm dealing with just a plate and its surroundings, the only thing the plate sees is its surroundings. So shape factor in that case would be 1. May need to worry about things in terms of epsilon. So if it's 1 or not 1, things of that nature. So again, very basic parts of each radiation, convection, and conduction. In that second part, which ones do you use, which ones do you want to use, which ones do you need. First part, again, is the overall, what's going on, what do I need to include in terms of, should I include free convection or not? Should I include that fact that this object's heating up or cooling down? Do I need to include that? So that is where your final exam is going to go. So again, it's 1 question. First part, what modes of heat transfer do I need to include? What assumptions have I made? What's my overall governing equation? And part 2, kind of the details. How am I actually going to calculate those convections and conductions and radiation terms? And hopefully get a final overall answer. So that is end of the course. So hopefully it all went fairly well, even this weird transition time, half of it being online, half of it not being online. I hope you had fun, hope you enjoyed it. And I guess I won't see you for the final, but I will virtually see your grades for the final. And as I said, hope you had fun.